Jai Hind everyone. I Neeraj Sharma, Assistant Professor EC Department at Akgec Engineering College, Ghaziabad. I am before you to present the video lecture for the complex topic series for the subject digital signal processing. So, in this lecture, I have the topic selected for this lecture, that is the decimation by a factor capital D here. So, as per the introductory part, as we can see here, the system that use single sampling frequency for analog to digital conversion, that is simply called as a single rate system here. But many practical applications such as software assigned radios, teletype, facsimiles, digital videos and audio, the different sampling rates are used to process the various signal corresponding to their bandwidth here. So, the major concern that comes here, that is the what about the solution for the if we are using the different sampling frequency. Okay. So, how can it be possible? Because every function use the different frequencies for the transmission and their respective corresponding bandwidth. So, the solution for these in this case can be will be carried out with the help of multi-rate digital signal processing. So, the multi-rate digital signal processing is required in digital system where more than one sampling rate is needed here. So, that means when we are operating with the other than single sampling rate, the system said to be a multi-rate digital system. So, for example, here it has been said here in digital audio, the different sampling rates are used as a 32 kilohertz for broadcasting, 4.1 kilohertz for compact discs and the 48 kilohertz for audio tape. So, in the digital video, the sampling rates for composing video signals are 14.318118 megahertz and 17.1344 megahertz for NTSC and the PAL respectively. So, that means for a single audio signal as well as in a single video signal, for the different purposes which has used simultaneously throughout the communication, that using the different sampling frequencies here. So, how can it be possible for to transmit or to for the communication? For that point of view, the multi-rate signal processing will provide a very fine solution here. Okay, but the sampling rates for digital communication signals are the 30.5 megahertz and 6.75 megahertz for the luminescence and the color difference here. So, we can see there for a single, as earlier I said that for the different application for a simple single application, but they are using for the multitasking purpose, we use the multi-rate signal processing here. So, in this way, so the next question that has been arises here, that how can it be possible? How can we achieve this multi-rate sampling? This is a question mark. So, that means what can be possible here? Either we have to increase the sampling frequency, only the two possibilities will be there. For this, there should be increased or should be decreased here. Okay. So, how can it be possible? So, for that point of view, that means for the different sampling rates can be achieved using an upsampler, first one, and the downsampler. With the help of that means either we have to upsampler means we have to increase it, or downsampler means that is it should be decrease here. The sampling rate should be decrease here. So, the basic operations in multi-rate processing to achieve this upsampling and downsampling are decimation and the interpolation. So, the process with the help of we can upsample or downsample the signal with the help of interpolation and the decimator respectively. In the decimation, what is going to be happened here? That means the sampling should be decreased, sampling rate should be decreased. In the interpolation, the sampling rate should be increased here. So, here I have considered the decimation. So, the decimation is for reducing the sampling rate and interpolation is for increasing the sampling rate. The sampling frequency increase or decrease without any undesirable effect of error due to the quantization and the aliasing. So, while designing multi-rate system, the effect of aliasing for decimation and pseudo images for interpolation should be avoided here. So, the two things that can be arrived come into the picture, that is the when we are designing any decimator, the device for the purpose of downsampling, that means the decimation, what will happen, because if we have considered that any sequence in the xn in a time domain sequence, it is having any sequence xn. So, when it will be downsampled, that means we are what going to in the time domain we have to reduce it, but in the frequency domain what it will be happen, it should be increased here. In the same meanwhile, in the interpolation in the time domain we are increasing its sequence length in time domain, but in the frequency it should be decreased here. So, but in the case of the decimator, what will happen when we are providing, let us say any sequence will be here. So, we are providing it what we can say xn any sequence when we are decimating in by some factor x of n of d here. Okay. So, what will be happen, the time domain sequence has been reduced here. Okay. In the for in case of interpolation, the interpolation will be performed by this equation, xn should be replaced with xn upon I. So, when it is specifically we will think about for the decimation, the time domain expression should be decreased, in the frequency it will be increased. So, what will happen when the number of samples will comes out, so the problem aliasing may be increased here. So, in that process what will happen, the decimator, while designing any decimator circuit, the input should be applied which should be alias free. So, for that point of view, before applying any decimator to any system, the first of all before the decimator, the anti-imaging filter, anti-aliasing filter should be imposed here first of all, then it will be converted, output should be provided to the decimator, so that the aliasing should be reduced here. In the case of interpolator, what will happen, where when the interpolation will be performed, so the number of mirror images has been introduced between the two successive sequences. So, in that way, so there is a requirement to remove the mirror sequence and to get our actual information, So, in that point of view, the anti-mirror filter should be imposed here. So, here a statement is written that while designing a multi-rate system, the effect of aliasing for decimation and pseudo images for interpolation should be avoided. So, now in this lecture I will focus on to the decimation by a factor d. So, for that point of view, we can see here, let us assume that the signal x of n with a spectrum x of omega is to be downsampled by the factor d here. That means xn n into let us say simple xn, its transform frequency responses of x of omega here, when it will be downsampled. So, what will happen, the frequency response should be x of omega by d here. So, in this case, the x omega is to be downsampled by an integer factor d here. So, the spectrum of x of omega is assumed to be non-zero in the frequency range interval from 0 to omega, omega will greater than 0, but less than equals to pi here. So, if we know that if we reduce the sampling rate simply by selecting every dth value of xn, the resulting signal will be an aliased version of xn with a folding frequency of fx by 2d. So, to avoid this aliasing, the aliased version, this has been arrived. So, for the point of view, we must first reduce the bandwidth xn already, because frequency response getting increased. So, what we will do here, we will just compress already. It is become the, we have to reduce the bandwidth here. So, it will be compressed now. So, that can be possible with the fx should be when we keep fx by 2d or equivalent to omega max equals to pi by d here. So, we may downsample by factor this d here and thus avoid aliasing. So, in that case, the circuit will be the block diagram for any decimation will be given by this block diagram. So, this is the picture which represent the decimation by a factor D here, where the first of all input should be xn will be applied to the filter is where is anti-aliasing filter, which impulse response is h of n, then we will get the output v of n. Then now it will be this output when it will get after that applied onto the downsampler, where this downsampler will downsample this input vn by vd by the factor d, and after that we will get at the output ym, where the output frequency fy is equals to what? The downsampled of the input frequency here. So, here we can now again see that the input sequence xn is passed through a low pass filter. So, for its derivative part, what the output value of ym here? What is the output value ym here? So, for that point of view, the input sequence xn is passed through a low pass filter first of all, which is characterized by the impulse response hn, and the frequency response, that is the sd of omega, which is ideally satisfy the condition what? That sd of omega is 1 for the mod value of omega less than equals to pi by d, otherwise 0 otherwise. Thus, the filter eliminates the spectrum of omega in the range of omega from greater than pi by d but less than pi. So, the implication is that only the frequency component of xn in the range of this omega, where it is less than equals to pi by d, are the interest to further processing the signal. So, the output of the filter of the sequence Vn is given as this one, the output which is the convolved impulse response convolved with this xn. So, we can write it here like V of n is equals to summation of k is equals to 0 to infinite h of k into x of n minus k, because simply in LTI system the output when applied to with the impulse response, the output is then convolved. The output is now convolved, input is convolved with the impulse response. So, we can get here hk into x of n minus k, which is then downsampled by the factor d, this one here now applied onto the downsampler d to produce this output ym. So, ym is equals to what? Ym is equals to what? The down v of n into d here. That means the input which is applying here n into d and vn downsampled. So, output we will get y max is equals to v of n into d here. So, we can write it here for the, if we are writing it for ym. So, it will be written as ym of d, sorry, here. So, ym is equals to what? Vm d, v of m into d. So, what v is what? V is this. We have applied onto this equation here. So, the ym value is equals to summation of k is equals to 0 to infinite hk x of md minus k here, because this n is downsample, which is replaced by m into d for the downsample. So, how it is possible? How can for the pictorial point of view we can now see here. So, the frequency domain characteristics of the output sequence ym can be obtained by relating the spectrum ym to the spectrum of the input xn. So, how can be possible? Here we have written that v of n. What is this? This is an input which is applying onto the decimator, that is equals to Vn. Let us say consider where the n is equals to 0 plus minus d, 0 ranging n is ranging from 0 comma plus minus d plus minus 2d etc. otherwise. So, clearly we can say that Vn can be viewed as a sequence obtained by multiplying this Vn with a periodic train of impulse Pn with a period d as illustrated in figure. So, you can see in this picture here, this is an Vn value, this you can a discrete value for a sequence xn you can see here. After that, now it can be downsampled with a factor, with a function p of n. That is, we are applying with the Pn, that is in a rectangular periodic train of impulse p of n with period d here, as you can see. So, the d of here you can see that 2 for this. So, the output Vn, that is the multiplication of these two Vn into Pn. So, the output this is the value for the Vn. Then now it can be downsampled, Yn is equals to V cap of n into d. This n will be replaced by this nd. So, that means ultimately what is going on? We have to apply onto this V and D. So this will be the final result for the downsampled here. So as you can see that how can the downsample can be performed in this way. So this is the figure, just simply illustrate the steps required to facilitate the mathematical downsample by factor D using a sinusoidal signal sequence for a reference here. So now what we have to do, the discrete Fourier series representation of this sequence Pn, that is like an anti-aliasing filter here. So Pn is equals to, we have considered 1 upon D, summation of k is equals to 0 to D minus 1 e raised to power j 2 pi k into n by D here. So the V cap n here, it is Vn into Pn, and Ym is what? V of this Md, n will replaced with Md for the decimator. So then it can be write V of Md into P of Md is equals to V of Md here. Now what will be going on here? Let me think and discuss about it. So the V, because we have to go for this frequency response here, that what we are looking in the time domain, what happened in the frequency domain. So for that point of view, now the Z transform of the output sequence, this Ym, we have to take its Z transform. So Yz, the definition of the Z transform is equals to Yz equals to summation of m is equals to minus infinite to infinite y of m into z raised to power minus m is equals to what? What is the value of this Ym? This one we have to put here. M is equals to minus infinite to infinite v cap m into d z raised to power minus m. This equation will become like this. After that, now we have considered that is another factor, let's say m. So m is equals to md. So this can also be replaced here. So the above equation now can be looks like this one, y of z is equals to summation of m is equals to minus infinite to plus infinite v cap of m into z raised to power minus of m upon d here. So let me our next one. Now we put the value of v cap of m here, that is m is equals to minus infinite to infinite vm. Because in this Vm is what? Vn into this Pn. The value of this Pn we have to, this one value we put here. So Vm into 1 upon D, summation of k is equals to 0 to D minus 1 e raised to power j 2 pi mk upon D into z raised to power minus of m upon D. Now we have to just change the summation here, summation sign 1 upon D, k is equals to 0 to D minus 1, m is equals to minus infinite to plus infinite Vm, and this factor should be merged with this one z. So it can be written as e raised to power minus of j 2 pi k upon D into z raised to power 1 upon D into raised to power of minus m here. We can now just simplify here. So what will happen here, if we will see for this one, if we see for this one, what is this? If we relate this one, this expression with the expression for the z transform of ym, that is yz is equals to m summation m is equals to minus infinite to plus infinite ym z raised to power minus m. So we can see that the what will be happen here, this also a z transform of a function e raised to power minus j 2 pi k by d z raised to power 1 upon d. So this expression can be now written as what? 1 upon d, k is equals to 0 to d minus 1 v of e raised to power minus of j 2 pi k d z raised to power 1 by d. It can be simply write it like this. Then what is the v? V initially what? V is what? Vz is equals to hdz into x of z, the output which is applying onto this decimator. So this one, as you can see here, this one Vz. So we can also write the equation y of z will become 1 upon d, k is equals to 0 to d minus 1 hd, z will replaced with by this variable here in this or also in factor x, hd into e raised to power minus j 2 pi k upon d into z raised to power 1 upon d into x raised to power e minus j 2 pi k upon d z raised to power 1 upon d. Let's say this is the equation number a here. So now what? We can conclude that the spectrum y of omega y, which is obtained by spectrum y of y from this equation A on the unit circle the expression can be expressed as what? Y of omega y is equals to 1 upon d summation of k is equals to 0 to d minus 1. Here h of d omega minus 2 pi k upon d into x of omega y minus 2 pi k upon d here. So, sorry, it is also an omega y. So, let us say this will be the equation, that is the response of output when we are applying any decimator, when we are performing it with the help of some decimator. So, with now for properly designed filter, let us say here what will happen if let us say value d is equals to 3. So, what will happen, this ranging from 1 upon 3 k is equals to 0 to 2 here. So, first of all we will expand it for k equals to 0, where we are not getting any expression, but when put value k equals to 1, so the expression we will get hd of omega y minus 2 pi upon d. For 2 we will get hd of omega y minus 4 pi. So, in this way the frequency is shifting and also get the aliasing will be come. So, in that properly designed filter, where the aliasing, that means the aliasing is eliminated in, so the first term will be vanishes from the equation B. So, the output will become V y of omega y is equals to 1 upon d hd of omega y by d into x of omega y by d here. So, this will be the now the final output, or simplify, we will simplify it. So, we can write it V of y omega y is equals to 1 upon d x of omega y by d here. So, these are the output we will get for the after the decimation, where the range of omega will be equals to y pi. So, this will be the final calculation when we are decimating any sequence, input sequence x n by factor d here. So, although let us say some pictorial view you can see here, that let us say if we are in frequency response of any signal from minus pi to plus pi for the range omega x here, this one let us say, where this x of omega x input, then what will be the output for the HD? We have considered that pre-designed filter case. In case, what we will do in this case, let us say we have selecting impulse train like this, minus pi by d to pi by d, this is pi, this is from minus pi to pi. So, this will HD of omega x So the output that after that input xn applied to the impulse response, this is an impulse response output. So the output Vn of n, the V of n presentation will be, this is the multiplication of these two here, sorry. This is ranging from, this is the response when it will output is multiplication of these two, that is V of omega x. Then when it will be downsampled by factor d, the output ym, it will be get where the frequency response is omega y here. So it can be expanded. So that is a figure for the y of omega y here. It is ranging from 0 minus pi to pi here, like this. So this is the simple and spectrum of the any signals when it is decimated by factor d here. So in that case, in this way, the how the decimation can be performed, we can see here. Then the aliasing effect and the aliasing filter we will see. So we can find that the spectrum obtained after the downsample will overlap if the original spectrum is not band limited. So it will pi by 2. So the overlapping spectra is called then aliasing. So therefore aliasing due to downsampling signal by factor d is absent if and only if the xn is band limited by this factor. As you can see here, this that we have applied here, this one. So if the signal xn is not band limited to plus minus of pi by d, then a low pass filter with a cutoff frequency pi d used prior to downsample. So this low filter which is connected before the downsampler to prevent the effect of this aliasing by band limiting the input signal is called as the anti-aliasing filter here. So as you pictorially you can see here, if we have to apply any sequence here, x of omega will be this from let us say x of omega, it is expanded version for xn, that is from 0 to 2 pi by d, this one. So when output we will get, the signal can be mixed with each other, so that this type of aliasing at this point, because when it will be comes out another response that can be overlap. So this is named as an aliasing. So in that way we have to remove this part while designing any anti-aliasing filter with the when the after that output is applied onto the downsampler. So the response should be like this one, as trend you can see here. So this is from my side for the decimation by factor d. So I have chosen the take the reference of the book John G. Prokes for while presenting this this video lecture. Thank you and Jai Hind.